Welcome viewers to the NPTEL lecture series on the calculus of variations. This is the 13th lecture in the series. In the last lecture, we had discussed isoperimetric problems. Now, we will discuss in this lecture the problem of finding geodesics. Geodesics are defined as the straight lines on certain surfaces. That means, when you stretch those surfaces as flat surface, then these will reduce to straight lines. So, they have the minimum length, that means in the neighborhood of these curves, if you consider any other curve joining two given points, then that curve is having the least length, that is what is called geodesics. Now, this can be described geometrically like this, that you have a domain D in xy plane, and this is the surface. This is described by like this z of function of xy. So, here there are 2 points given A and B, and a curve joining these 2 points A and B lying on this surface. Now, we want to find that curve on this surface joining these 2 points, which will have minimum length. So, that is what will be called geodesic on this curve, this surface given by z equal to z of x y. So, here we will take the example here like this. So, you will have this functional I of x y z, and here this will be joining 2 points, let us say A and B, and then this arc length on this surface is given by ds, and this will be integral a to up to a to b, and square root of dx square plus dy square plus dz square. So, if you parameterize this x as x of t, y as y of t, and z as z of t, such that on this surface z t is given as a function of x t y t like this. So, here you can see that then here this I x y z then will be given. Here t will have this range t1 less than equal to t less than equal to t2, t1 to t2 square root x dot square plus y dot square plus z dot square and dt. Here x dot is dx by dt, y dot is dy by dt, and z dot is dz by dt. And here this x, y and z are satisfying this relation. So, that is what we will have. More generally, we can have the following situation here, or this z t, z dot t will actually be then z x x dot plus z y y dot, and so I of x y z will be given by t1 to t2 square root x dot square plus y dot square plus z x x dot plus z y y dot square dt. So, this is functional of this type t1 to t2, where f here t does not appear explicitly, only x, y, and because this z x and z y will be functions of x and y. So, and x dot y dot dt. Here t does not appear explicitly. So, it is of this type, and so you can see that here you have Euler's or system of Euler's equation given by f x minus d by dt of f x dot equal to 0, f y minus d by dt of f y dot to 0 here, because you have only x and y are appearing in this, and x dot y dot. So, let us take this example. We know the answer of this. Let us take this sphere. So, our surface as here is given by x square plus y square plus z square equal to a square. So, this is sphere here, and so we parameterize this x as a sin theta cos phi. Here any point P on the sphere, you can see that this vertical angle is theta, this angle is theta, and this horizontal angle is phi. So, x, y, z are given like this: a sin theta sin phi and z equal to a cos theta, because here P is OP is equal to A, and when we project it here, so let us say this is P dash. So, OP dash is A sin theta, and so and let us say this one is P double dash, and OP double dash, that is the z coordinate, that is A cos theta. And so, this x coordinate will then be, let us say this is L and this is M, then L P dash is, that is the y coordinate, which is A sin theta sin phi, and projection of OP dash on y axis, similarly OL equal to A sin theta, sorry, this is phi, sin theta cos phi. So, that is what is the parametric representation here, and here phi is ranging between 0 to 2 pi, and theta is ranging between minus pi by 2 to plus pi by 2. So, here on this surface, so we have now situation like this. And given any 2 points here A and B, so this will be the kind of curve on this surface, and we want to find the minimum length curve on this surface. So, here we see that ds square is dx square plus dy square plus dz square, and this is equal to a square cos theta cos phi d theta minus sin theta sin phi d phi square plus a square cos theta sin phi d theta plus sin theta cos phi d phi square plus a square sin square theta d theta square. Squaring and summing it up gives us the following, that is a square d theta square plus a square sin square theta d phi square. Hence, this the length here, then x. So, here it will be then function of theta and phi now only. So, here I of, so the length of this, that's dependence will show later. Here this is some the independent variable, here we will take as theta as a function of phi, and so we will have square root 1 plus a will come out and sin square theta, and we will have d phi over d theta square and d theta. Here we treat that phi as function of theta, because here on this surface is described by these parameters theta and phi. So, a curve on this surface will be function of one of the variables, either phi as a function of theta or theta as a function of phi. So, we can take any one as independent variable. So, here theta is independent and phi is dependent variable. So, this is the functional we have here, which gives the length of so here it will be function of this phi, and so that is what we will write it as I phi, and this is lying between two angles here, theta 1 and theta 2. Integration over theta lying between theta 1 theta 2, where they will be describing theta 1 will be for this A and theta 2 will be for B. So, that is what we have here. So, for this f is now a square root 1 plus sin square theta phi dash square, where phi dash means d phi by d theta. So, here this is function of theta and phi prime. Phi does not appear explicitly. So, here we will have the Euler equation. See, Euler's equation implies f phi minus d by d theta. In place of x we have theta, f phi prime equal to 0, and here f phi is 0. So, we get minus d by d theta of f phi prime equal to 0. This implies that f phi prime equal to C1. So, first integral is readily available here, and that is f phi prime equal to C1. Now, f phi prime in this case is a sin square theta phi prime over square root 1 plus sin square theta phi prime square, and this is equal to C1. So, simplifying this, squaring and solving it for phi prime gives you, so solving for phi prime we get phi prime equal to C1 over sin square theta square root a square sin square theta minus C1 square. So, here we integrate it here. So, like this. So, phi equal to, so this can also be written like this, d theta over sin square theta square root a square over a C1 square. This dividing by C1 square will cancel, dividing by C1 here will give us this, and taking out this sin square phi will give us the following, minus cosec square theta plus some C2 here. So, this can be simplified, and d theta cosec, we can take this up there, cosec square theta over square root a by C1 whole square minus 1, and then writing it as 1 plus cot square theta. So, that is what we will have. So, then putting u equal to cot theta gives us, put this, we get this as, so phi as du over square root a by C1 whole square minus 1 minus u square plus C2. So, that is sin inverse u by square root a by C1 whole square minus 1 evaluated at theta 1 to theta 2 here. So, plus, so here then substituting back we get the following. So, phi will be then sin inverse u over a by C1 square minus 1 plus C2. So, taking the C2 here, so phi minus C 2 and then taking sine of this equal to u by some thing. So, let us say this is C 3 u, which is C 3 then cot theta, which we can write as C 3 cos theta over sin theta. Simplifying this here and taking sin theta here. So, sin phi sin theta and this cos C 2 minus sin C 2 cos phi sin theta equal to C 3 by A. Here also we can take by A like this, by A cos theta. Now, substituting back we get here some constant A y minus this, also we can write plus B x, and this is minus C z, and so we get A y plus B x plus C z equal to 0, and equation of a plane, that is hence x y z lie on a plane as well as on the sphere x square plus y square plus z square equal to a square. So, the intersection is section of these two is a great circle. So, we get the answer as great circle. So, joining these 2 points, the least length would be achieved when the curve is a part of great circle. So, that is what we get here in this case. Now, let us generalize this, because here we had a very special case, and in general we have situation like this, that we have some functional I 0 as x y z, which is t 1 to t 2, some functional f integrand of the functional is function of x dot, y dot and z dot only, and these points x y z lies on a surface given by some this g x t y t z t equal to 0. Here t 1 less than t less than equal to t. So, we apply the Lagrange's method. We use Lagrange's method of undetermined parameter So, we consider this I x y z as t 1 to t 2 f 0 x dot y dot z dot plus some lambda t. Here lambda will be a function of t in general, x t, y t, z t. So, here the integrand is f, which is f 0 x dot y dot z dot plus lambda t g of x t y t z t. And so, we get the system of Euler's equations are f x minus d by dt of f x dot equal to 0, f y minus d by dt of f y dot, and f z minus d by dt of f z dot equal to 0. So, here these give us here f x will give us g x here, lambda times g x. So, that is what we get, lambda t g x and minus d by dt of f x dot equal to 0, lambda t. So, solving it for lambda t, we get from here lambda t equal to d by dt of f x dot over g x. Similarly, here g y minus d by dt of f y dot will give you lambda t equal to d by dt of f y dot over g y. And third equation, f z dot equal to 0 will imply that lambda t equal to d by dt of f z dot over g z. So, we get d by dt of f x dot over g x equal to d by dt of f y dot over g y f z dot over g z. So, this is what we get in this case, in general case, and let us call it 13.2. So, in particular in this case, so if we consider the earlier example of a sphere, so we have in the case when we have sphere as the surface, we get this I 0 as I 0 of x y z as t 1 to t 2 square root x dot square plus y dot square plus z dot square dt, and g x y z as x square plus y square plus z square minus r square or a square. So, here we get this I of x y z as t 1 to t 2 square root x dot square plus y dot square plus z dot square plus lambda t x square plus y square plus z square minus a square d. So, here we have f as x dot square plus y dot square plus z dot square plus lambda t x square plus y square plus z square minus a square. So, here we get f. So, the equation we have d by dt of f x dot over g x equal to d by dt of f y dot over g y d by dt of f z dot over g z. So, that is what this will imply. That is the number we had given 13.2. So, this 13.2, that is, this implies that d by dt of f x dot gives you this 2x 1 over root 2 this thing, and then you get 2 x, and so 2 cancels here. So, x dot over square root, this is f 0, not f actually, this should be, because f 0 because only f 0 involves x dot, y dot, z dot here, and so we have in this should be d by dt of f 0 here. Okay, here this will anyway give us this equation will give us this f 0 dot here. So, that is what we have, f 0, f 0, f 0. So, f 0 here is square root x dot square plus y dot square plus z dot square. Sorry, this should not have been like this. You have to correct this. It should be square root x dot square plus y dot square plus z dot square plus lambda t of this. Square root is only up to here, that is x square plus y square plus z square minus a square. So, this is what we have here, and so whether we write f 0 or not, it does not really matter. We will have the same result here, because this x dot, y dot, z dot are involved only in this f 0 part, and that is why we get f 0 here. So, we get this x dot over this x dot square plus y dot square plus z dot square d by dt of this, and this over we have this gx is this one, that is lambda t. Lambda t is gone anyway, only gx is this one. So, we get 2x and then d by dt of y dot over square root x dot square plus y dot square plus z dot square over gy means 2y, and this is equal to d by dt of z dot over square root x dot square plus y dot square over 2z. So, simplifying this will give us the following. So, here we have, so we get in this case d by dt of x dot over f0, and this is d by dt over x, and d by dt of y dot over f0 over y, d by dt of z dot over f0 over z. And so, opening this, we get x double dot f0 minus x dot f0 dot over x f0 square y double dot f0 minus y dot f0 dot over y f0 square z double dot f0 minus z dot f0 dot over z f0 square. So, simplifying this, solving it for x over y, we get x double dot over f0 minus x dot f0 dot, here this over this y double dot f0 minus x dot, sorry, y dot f0 is x over y, and now cross multiplying and then solving it for f0 dot over f0, we get x double dot times y minus x dot y double dot here, and then over x dot y minus x y dot equal to f0 over f0 dot over f0. Here f0 is square root x dot square plus y dot square plus z dot square. And so, this is also solving it for the other two, y double dot z minus y z double dot over y dot z minus y z dot. Now, the numerator is the derivative of this, since x double dot y minus x dot y double dot is d by dt of x dot y minus x y dot, and y double dot z minus y z double dot equal to d by dt of y dot z minus y z dot. So, integration gives you ln of this x dot y minus x y dot, absolute value of this, and ln of y dot z minus y z dot plus some ln c, and so raising it to exponential, we get x dot y minus x y dot over y dot z minus y z dot equal to c. Now here so again cross multiplying and solving it for, let us say we can write it here in this manner, that x dot plus c z dot over x plus c z equal to y dot. So, this implies, so again integrating here, now this gives you ln mod x plus c z equal to ln mod y plus ln d. So, we get here x plus c z over y equal to d, and so x plus c z minus dy equal to 0. So, this gives you equation of a plane. So, x y z lie, this point x y z lies on a plane. Also x y z are on the sphere, hence x y z moves on an arc of a great circle. So, we get the same result, but in a different manner. So, here like this we can have these equations solved, and now we move on to certain problems where boundary points will be moving. So, what we have so far, that a functional like this I y equal to x 0 to x 1 f x y y prime x, so dx, where this, rather we took x 1 to x 2, where y at x 1 is y 1 and y at x 2 is y 2, where the points A, which is x 1 y 1 and B x 2 y 2, we have dealt with the functionals like this, where this the points are fixed. Now, we shall consider the functionals here. Let us say we shall consider the functionals where A x 1 y 1 or B x 2 y 2 are moving, or both A x 1 y 1 and B x 2 y 2 are moving. So, these problems are called moving boundary value problems. These problems are called problems with moving boundaries. Now, so here situation is like this. you have this point A and B, and let us say this is the curve joining them. This is x1 y1 and this is B x2 y2, and these points are moving. So, next one curve could be like this, other curve could be like this. So, A moved here, so that is A x1 dash y1 dash, and B has moved here, B x2 dash y2 dash. Or situation could be like this, that only A is fixed and here both A and B moving, A and B moving. Here A is fixed, B is moving. So, A is x1 y1, B is x2 y2, and now B has moved here. So, B x2 dash y2 dash, and it can move like this. So, B x2 double dash y2 double dash. So, B is moving here freely, or it may move along a curve. So, it may be constrained movement or it may be a free movement. Here also A can move on a curve or on a surface. Similarly, B can move, if it is a higher dimensional problem, then it can move on a surface also. Here in 2 dimension case, they may move freely in the plane or they may move along the certain given curves. So, those will be constrained movements, and we will be considering these type of functionals where either both the points are moving or one point is moving, and we will be dealing with various kinds of functionals where such movements will take place. So, that is what we are going to have here. And so, let us see the simple case. First we start when A, that is x1 y1 is fixed. So, that is what we will take here when A x1 y1 is fixed and B x2 y2 is moving. Now, whether both A and B are moving, then suppose that this I y takes, so this is what we had here, I y. So, I y, suppose that I y takes the optimal value on a curve y which passes through A x1 y1 and B x2 y2, when these points are moving, then this y also optimizes I y when we consider these A x1 y1 and B x2 y2 fixed. Hence, y must satisfy Euler's equation, which is a necessary condition, that is f y minus d by dx of f y prime equal to 0. So, here the solution of this is a 2 parameter family of curves y as y x c1 c2. So, if a this x1 y1 is fixed, then one of the constants C1 C2 is determined, hence in the case when B is moving IY can take optimal value on an extremal only, that is one of the members of the 1 parameter family of curves y equal to y x c which is a subfamily of, so let us say here we had given numbers. So, let us say this is 13.3 and this is 13.4, this is subfamily of 13.3. Because one of the constants there from C1 C2 is determined, that we will denote as C, and so we get this subfamily from this. So, we need to consider, we would consider only I y, which is the function, and it will be function of parameter c also, like this. So, you have x1 to x2 f of x y x c and y prime x c dx. So, we will find the optimal value of this over the family of. So, we will be doing all the calculation here over the family of this 1 parameter curves given by 13.4, which are the solutions of this Euler's equation. So, that is what we are going to consider, and here we will be considering the variation of this functional, and we will restrict our analysis, our calculations wherever this y appears, even though we may not be denoting this dependence on C, but wherever we consider this I, subsequently this y will be actually the solution of the Euler equation. So, that is what we are going to consider in the next lecture. Thank you very much for viewing this.